Welcome back. Today we will be talking about fundamental counting principles. Um, so fundamental counting principles can be used to determine the number of possible outcomes when there are two or more characteristics are there. So there are multiple independent events are there, and when the independent events are there, we can use fundamental counting principles. So keeping that thing in mind, uh, for instance, we have for independent events, we have A and B, and the outcome for A is N and outcome for B is M. So to find the total number of outcomes, I can multiply N times M because they are two different independent events. So N times M outcomes for events A and B all together if I combine those two together. For example, we have how many ways can you arrange the letter A and B? That is a case of fundamental counting principle. The another thing is called permutation. Permutation, the catchy phrase is picky about order. So order is the priority. So how we are ordering the objects, that plays a crucial role. So the number of permutations of our objects taken from a group of n distinct objects is denoted by this formula, which is NPR, which is nothing but n factorial. That means the total number divided by n minus r factorial. So r is the outcome that we are looking for. And this sign, the explanation sign, is called factorial. So just a quick recap. If I have to find out 3 factorial, it is nothing but 3 times 2 times 1. So the number and the number preceding it multiplied together. So the possible type of questions can be like this. There are 7 teams competing for an event. How many ways can teams be awarded for the gold, silver, and bronze? So to award gold, bronze, and silver, we need an order. If you're getting gold, that person is not getting a silver or the bronze, right? So the order is important. Let's take one example, and we will solve it 2 ways with fundamental counting principle and permutation. So I guess you might have read the question. So they are asking for the first, second, and third position. So let's start with fundamental counting principle. So for the fundamental counting principle, let's say for the first prize, how many horses are there for the first position? We have 8 are there, right? So for first, I have 8 choices. Now, first position is taken care of. How many are left for the second place? 7 choices are left. Now, second position is also taken care of. How many are left for the third? Only 6 are left. So these are independent event. First choice, second choice, and third choice. So going back to the fundamental counting principle, when we have independent events, the outcomes of each and every independent event can be multiplied together to get the possible number of outcomes, a possible number of altogether outcomes. So we have for the first position, we have 8 choices. For the second, we have 7 choices. And for the third, we have 6 choices. Let's multiply them together because they are working as the outcome of 3 different independent events. 8 times 7 times 6, that will give you 336 possible outcomes, assuming that there are no ties. Now let's approach the same problem with the permutation. So permutation says NPR. N is the total number. So total choices are 8. Out of the 8, how many choices we are looking for? We are looking for only 3 choices. Position 1, position 2, and position 3. So my equation will be 8P3, which is nothing but 8 factorial divided by 5 minus 8 minus 3 factorial. So that will be 5 factorial. So 8 factorial divided by 5 factorial. Now 8 factorial contains a 5 factorial. So I can rewrite 8 factorial as 5 factorial times 6 times 7 times 8. Why we are writing it down this way? So that I can cancel out 5 factorial from the denominator. And that will result into the same equation that we got for fundamental counting principle. So whatever approach we apply, the answer will remain the same. So in some of the questions, they will really ask you, okay, you have to use only fundamental counting principle or permutation. So the another type of permutation is called distinguishable permutation. So as by theory, when a set of n objects has n n1 of one kind, n2 of a second kind, and so on, then n can be represented as the sum of all the kinds, n1 plus n2 and so on. So the permutation will be n factorial divided by the product of all of these kinds, factorial of all of these kinds. Now, the questions will be very, very simple. The theory might confuse you. If you read this question, in how many distinguishable ways can the letters in this particular word can be written? So how will I approach it? I will count how many times one particular letter is repeating. So as you can see, I is repeated how many times? I is repeated twice. So that is my n1 object, right? So total number of n and then n object. How many letters are there? We have 7 letters. And after that, I is repeated twice. So n1 is 2. N is repeated again twice. So n2 is also 2. And moving forward, A is also repeated twice. So n3 is 2 again. Right? So again, just as a recap, we are trying to find out how many letters are repeated again and how many times they are repeated. So total number of letters in this word is equal to 7. So that is your n. n1 is the I component, which is 2. n2 is the n component, which is 2 again. And n3 is the A component, which is, by chance, it is 2 again. So in this case, we have all the 3 components as 2, 2, 2. In some other scenarios, it might be a different number. So let's put it in the equation for distinguishable permutation. So we want n factorial divided by, we have 3 components. So we are multiplying n1 factorial times n2 factorial times n3 factorial in the denominator. So we have 7 factorial divided by 2 factorial times 2 factorial again, and one more time 2 factorial. Now again, in 7 factorial, 2 factorial is already inbuilt. So I can expand 7 factorial as 2 factorial times 3 times 4 times 5 times 6 times 7. And this will help you to eliminate 1, 2 factorial from the denominator. Now, if you look at the numerator carefully, we have 4, and 4 is nothing but 2 times 2, and 2 factorial is nothing but 2. So in the denominator, we also have 4. So let's put it 2 times 1, and then one more time 2 times 1, and that will help us to eliminate 4 from the numerator. And we are left with only with 3 times 5 times 6 times 7. That will be 630. So this is called distinguishable permutation. You can try one question. Try about, let's say, the word banana, and then calculate on your own. Now, the third in this is called combination. So permutation was very picky about the order. Combination, it doesn't care about the order. So whatever order it is, it doesn't matter. So the combination of n objects taken r at a time is denoted by NCR. So we have n factorial. The pattern is the same in the denominator with n minus r factorial, but we are also multiplying with r factorial. So again, NCR is nothing but n factorial divided by r factorial times n minus r factorial. Let's take one example. So they are saying, in how many different ways can 3 letters be chosen from the letters A, B, C, D, E? So they are not talking about any particular order, what will come first, what will come second or third, and so on. So order doesn't matter. And when the order doesn't matter, we can safely use combination, that is NCR. So total number of alphabets are 5. and we are looking for choosing only 3 letters, any 3 random letters. So the combination implies order doesn't matter. So that is 5C3, not 6. So we have 5 factorial divided by 3 factorial times 5 minus 3 factorial. Now you know the drill, how to calculate the factorial. So quickly, we will be left with now 3 factorial is already inbuilt in 5 factorial. So the answer will only be equal to 10. Right? Let's take one more example. So in the next example, we have there's a glitch. Give me 1 second, let me fix it. Okay, here we go. So now in this case, we have this particular question. So each player is dealt with 3 cards from a deck of 52 cards. And they're asking for how many different 3-card hands are possible, right? Again, they are not talking about whether the cards should be given in an order. So the order will not matter. So the number of cards are 52, and we are looking for 3 cards. So R is 3. So it is a case of combination again. So 52C3 or NCR. N is 52 and R is 3 in this case. So you need to be very, very careful which case is the permutation case and which is the combination case. So 52CR, again, 3 factorial is inbuilt in 52. And same as 49 is also inbuilt in 52 factorial. So we will try to eliminate 49 factorial first. So we can say 49 factorial times 50 times 51 times 52 divided by 3 factorial times 49 factorial. Now this will help us to eliminate 49 factorial. And we will be left with 50 times 51 times 52, everything divided by 3 factorial. And 3 factorial is nothing but 3 times 2 times 1, which is just 6. So if you do the calculation, you should get 22,100 as your lovely answer. This is your happy chappy answer. Okie dokie. So the few key points. So is the order of the element important? So when the order of the element is important, that is a case of what? FCP, permutation or combination? It is permutation. Now let's talk about the second point. Are the chosen elements a subset of a larger set in which order is not important? When order is not important, that is a combination. And lastly, does the problem involve 2 or more separate events? That means separate independent events. That is the case of fundamental counting principles. So this is my simple way of making you understand this fundamental counting principle and counting principle in general. I hope it made sense, and I will see you in the next video.